My dear students, so until now we have learned about the structural isomerism. So in structural isomerism, you might have noticed that the structure is keep on changing even though the molecular formula remains the same. Correct? Now you can ask, sir, how the structure was changing. We can say that it was through the chain, the principal chain was changing. By that the structure was changing. So we called that isomers as chain isomers. Then we have observed that the posture of the double bond was changing. As a result of that, structure is again changing, but still the molecular formula is same. Then we say that those sort of isomers are position isomers. Then we have seen that the functional group itself was changing, but still the molecular formula remains the same. So we say that as functional isomers. We have seen ring chain isomers. All these, if you observe, will result in a structural change. What is basically a structural change? Structural change means one bond is broken or dislocation, the movement of one atom from one carbon atom to other, or complete relocation of atoms. This we can say it as structural change, or we can say structural change. Because of this structural change, we say there are certain set of isomers are there, that we call it as structural isomers. At the end of the day, isomers means compounds having the same molecular formula, but if they have different structures, we say structural isomers. That different structures can be due to many reasons, as we have discussed. Now we are going into a new term that is called stereoisomerism. Now structural, it's a easy word to understand. We can say, sir, because of so and so factors, structure was changing, so you called those isomerism as structural isomerism. Now you are using a term called stereo. This is not a common word that we daily encounter. This is a new term, stereo. So here, what do you mean by stereoisomerism, or what is the physical understanding of the term stereo means? That's what I am going to explain. Now listen here. Here also I am going to take two compounds which are having the same molecular formula, but however its orientation, for example, the location of atoms in space, that is differing. For example, if I can say an atom hydrogen H is present at a location 2,1 coordinate in an xy plane, I can take another compound where the same H is present in 3,1, but the same hydrogen atom is attached to the same carbon atom. Here also it is attached to the same carbon atom, but its orientation in space is changed. For simple example, I am taking these three pens. Okay, consider the joining point of this pen as the carbon atom. Now I know that if this is one compound, so I know that for this particular compound, you can see red color is projecting in Z direction, and I have the blue color projecting in X direction, and the black color projecting in Y direction. Now I can say, if I take another compound like this, now the difference is red color projecting in Z direction, blue color still have the X direction, but the black color is projecting in what direction? This is minus Y direction. So if you see, all these three are attached to the same carbon atom itself. There is no dislocation or there is no structural change, but the orientation of the atoms in the space has changed. That is what I am trying to say. So stereoisomers result, or stereoisomerism arises due to the different spatial arrangement of atoms in space. That is the most important understanding you need. Now the different question here is, sir, what are the different ways in which you can make different arrangement for atoms in space? What are the different ways you can implement this? I can say you can rotate it. Rotation will give rise to different orientation in space. Some people may say that it's not rotation alone. You can suppose if it is like this, you can make it upside down. Okay, so there is no rotation, just movement in the lateral direction. There are n number of ways. There are different ways. So based on that different ways, I am going to categorize this stereoisomerism. Okay. So what you can say stereoisomerism as a definition? I can say two or more than two compounds compounds having the same molecular formula, having the same MF stands for molecular formula, have the same structural formula also, same structural, because why I am saying same structural, because it is attached to the same carbon atom, so there is no difference in the structure. Having the same structural formula, okay, but what is going to vary? Can you tell me? But different arrangement of atoms in space. But different arrangement of atoms in space. So this is what is called basically stereoisomerism. Now the question here is, this stereoisomerism can be of two different types. What does that mean? That means you can arrange the atoms in space in two different means, or you can say it not in two different ways. I am saying by two different ways actually. So one mechanism we call it as configurational isomerism. So I can say, I will rub this, okay, I will rub this, and I can say classification of stereoisomerism. Okay, classification of stereoisomerism. So I can say this stereoisomerism is classified into this. You can compare with the structural isomerism can be of chain isomerism. You know that chain isomerism is a type of structural isomerism. So similarly, that structural change can be brought about by different ways. That is, one is changing the chain length, other is changing the position of the double bond. Similarly, this arrangement of atoms in space, different arrangements, that can be brought about by different actions. So one, we are saying it as configurational isomerism. I will explain what it is. Configurational isomerism. Okay, and what is next? I can say the next one is conformational isomerism. We say the next one is conformational. Okay, I should use blue color. Yep. So the other one is conformational isomerism. Okay. Now you will be curious, sir, what is this configurational isomerism? How this is going to create different arrangements of atoms in space? That is what I am going to tell. Okay. Now configurational isomerism means, here I can say the stereoisomer which cannot interconvert in each other at room temperature due to restricted rotation of double bond or triple bond. So such a type of configurational isomerism is called geometrical isomerism. And stereoisomerism, okay, configurational isomers, okay, which cannot superimpose on each other due to chirality, is called optical isomerism. I understood that you didn't understand anything. Okay, listen, I will explain. Now for that, let me tell, this configurational isomerism can be of two types. That is, one is geometrical isomerism. Okay, and the other one is optical isomerism. Now I will tell the fundamental, then you will understand. Now I am saying that this configurational isomerism is a group of compounds, or configurational isomerism is exhibited by a group of compounds which will change its, those atoms will change its orientation in space. Okay, they will change its orientation in space, but however it is not due to any rotation. That means there is a restricted rotation is there. Then those sort of configurational isomers are called geometrical isomers. So I can compare it like this. You can say, if you can see these two pens, okay, consider this as two pen itself. Okay, now you have a you consider here you have one carbon here, and you have the other carbon here. Now if I want to rotate this carbon with respect to the other carbon, because of the double bond, I can say I cannot rotate this one. You can see here, please listen to it. So I say, please, I hope you could see these two pens. Okay, now think like these two are double bond, one bond, other bond. Now think like this hand I am attaching here. This is one carbon atom, and this finger is my hydrogen, and this is also other hydrogen atom. Okay, you can see here. Okay, now you think similar thing is present here. Now different arrangements of atoms in space means I should rotate this. Correct? I should rotate this, but because of the double bonds I cannot do this rotation. Now the question here is, sir, why can't you rotate? Because of double bond also you can rotate, right? This we think in our normal sense, but this will not happen, because if you think, if there is only one bond is there, you know that bond is formed by sigma bond, that is formed by axial overlapping, so there is no problem in rotating. But when there is a double bond is there, one more bond is there, that is a pi bond, which have the p orbitals. You know that p orbitals are there, and there is lateral overlapping is there. You can imagine like that. When you have sigma bond alone, the overlapping is completely like this. Correct? You can think the carbon here overlapping is like that, and so that whatever atoms are here, you can rotate this with respect to this single bond. But whenever you have double bond is there, then the question here is, you have a p orbital like this, and you have another p orbital like this, and these two are interlinked. So if these are interlinked like that, can you rotate this? Can you rotate? No, not possible. That means there is a restricted rotation due to the double bond. Then the question is, sir, if we are not able to rotate it, then how the atoms will change its space, or how the orientation, how the different positions for atoms can come. It can come by naturally only. For example, if I am going to draw a compound like this, I can say C double bond C, and you have a CH3 group here in space. Say this location is 2,1, and this is hydrogen, and this is at position maybe 1,1, and you have another CH3 here at 2 maybe 4,1, and here you have another hydrogen which is at a position I can say, okay, 1,2. Okay, this is the coordinates I am saying. Now if I am taking another compound like C double bond C, okay, and which has its CH3 at the downside, okay, and hydrogen here, and here the hydrogen is here, but CH3 is here. Now if I am comparing these two compounds, you can see that to this carbon atom, maybe I say this is first carbon atom, this is second carbon. To the first carbon atom, CH3 and H is connected. Here also first carbon atom, CH3 and H is connected. To the second carbon atom, here CH3 and H is connected. Here also H and CH3 is connected. So structurally both are same, but the orientation of the atoms or group of atoms is different. That can be naturally, it might be like this. You cannot change this to this. I am not saying you can always convert one geometrical isomer to the another one. That is not possible. Just I am saying these two are, we can say, geometrical isomers. Both are having the same molecular formula, but the orientation of their atoms, or the atoms have different orientations in space. Okay, so this type of isomerism, which is due to restricted rotation of the double bond cannot here rotate, but naturally they are having different orientation of atoms. Such a type of isomerism is generally called configurational, that is by they are called configurational isomers. So under configurational isomers we have two options. One is the geometrical isomers, as I told, that is present between the double bond due to restricted rotation. So what I have told is with respect to geometrical isomerism. So this happens due to what? Restricted rotation, due to restricted rotation restricted rotation around double bond. Okay, around double bond. Now the next question is, sir, then what is the case of optical isomerism, sir? The question here is, in the case of optical isomerism, I can say that you can take the example of right hand and left hand. So if you see, structurally speaking, consider this as my central carbon. This has one thumb finger and 4 fingers are here. And if you take the right hand, that also has one central carbon and one thumb finger, all others are present. So if you are speaking structurally, both are similar. But if I am trying to superimpose this right hand on to the left hand, whether it is superimposing, what do you mean by superimposing? On superimposing, if both looks same, identical, then there is no meaning. But if it is not superimposing on this one, that means they have the different orientations in space naturally. If you see, the thumb finger of the right hand is naturally oriented towards minus x direction, but the thumb finger of the left hand is naturally oriented towards the positive x direction, but structurally both are looking same. So this type of compounds which cannot superimpose on each other due to chirality. Chirality, I will say, I will explain that. We can now think like this type of compounds which cannot superimpose on each other. They are referred to as optical isomers. Or technically we can say, if for example I can say this compound will rotate a plane polarized light towards towards clockwise direction. Think like that. Then I can say, if this is an optical isomer of this particular compound, then I can say this will rotate the plane polarized light towards anti-clockwise direction. This is how experimentally we can say these two are optical isomers or not. Understood? So I can say, then what is optical isomerism? I can say as a definition, isomers, or they are stereoisomers, compounds, I can write like that, compounds, isomers or compounds which cannot superimpose on each other. Okay, so compounds, we should not say compounds because all these are isomers. Both, if you take two compounds, both will be having the same molecular formula. So we can even use the term isomers, and even still we can say stereoisomers because there is no structural change. So we can say stereoisomers which cannot superimpose on each other are called optical isomers, and stereoisomers which have different orientation of atoms in space due to atoms in space, and there is a restricted rotation due to double bond. Those isomers are called geometrical isomers. Okay, I hope you understood. Next comes the conformational isomers. I will just say the definition. Conformational isomers, here between the carbon atom and carbon atom, there is only, you can think like this, between this is one carbon atom, this is another carbon atom, there is only single bond is there. Single bond is there means you have only the p orbitals in axial shape, correct? So you can rotate it, there is no problem, there is no double bond, so you can rotate this with respect to the other. So due to rotation, one carbon atom will have the atoms that will have different orientation every time. So that means there are infinite isomers if you rotate it, because you can rotate like 0.1 degree, you can rotate, then there is new configuration. If you rotate 0.2 degree, next you rotate. So there are infinite rotations possible. Understood? So conformational isomerism, it is a type of stereoisomerism which happens due to the free rotation of carbon atoms around a carbon-carbon single bond. We can say it like that. I hope you got a general idea regarding what is stereoisomerism. That is very important before we get into the topic. Otherwise you will not know what you are learning. You are learning something. You might be seeing this geometrical isomerism for years, but still you should get a grasp like isomers are simply two compounds having the same molecular formula. That isomers can be structural isomers if the structure is changing, but the two compounds we are comparing still have the same molecular formula. Now stereoisomers means both are having the same molecular formula, both are having the same structures, but their spatial location is changing. That location can be changing due to geometrical isomerism, because in geometrical isomerism there is no rotation, but naturally those two compounds have one group of atoms maybe in the upper plane, other group of atoms maybe in the other compound, that same group of atoms maybe in the lower plane. Then if you compare these two group of compounds which cannot even rotate, we say such group of isomers as geometrical isomers. Then optical isomers means again I can say here one compound cannot superimpose on each other. Here I am not speaking about any restricted rotation, nothing I am speaking about. I am just checking whether the given two compounds can superimpose or not. And also these two compounds should have the same molecular formula, correct? Of course, because we are speaking about isomers, and both are having the same structure, because now we are speaking about stereoisomers only, so they should have the same structures also. But again, when superimposing, we could understand that they cannot superimpose. That means any of the atoms might have different orientation in space. Now comes the conformational isomerism. Now initially the conformational isomers, the carbon atom to carbon atom, if you see, this is the initial position. Now if I am taking another compound that is having a different orientation like this, that is due to this rotation, then we can say these two are conformational isomers, because both are having the same molecular formula, both are having the same structure is not changing, but the relative position of the atoms is different. So these are the three different, we can say these are the different types of stereoisomerism, and I hope you got a fair idea. If you are not understanding, feel free to communicate the same thing in the doubt clearance group. Okay. Now let's look deep into what is called geometrical isomerism. Hi dear students. So in our last class we were just seeing the classification of isomerism. Then we have seen what is basically structural isomerism, we have seen it completely. Then we went to the stereoisomerism, its classification and definition I have explained. Now what is, we are going in detail. The first among that is geometrical isomerism. Okay, as I told already, what is geometrical isomerism? I told you that the geometrical isomerism, it happens due to restricted rotation around carbon-carbon double bond. Okay, it may not be carbon-carbon, it can be nitrogen, any other elements also. But the thing here is, you have a double bond here. These two ends are carbon atoms, and you have some atoms in the upper plane, some atoms in the lower plane. Here also you have some atoms in the upper plane and some atoms in the lower plane. But if you take a similar compound, it may have the atom here, let it be atom here, maybe A. The same A may be in the down plane for the other thing. In that case, we say this molecule and that molecule are generally, we call it as geometrical isomers. And you need to remember one thing here, you cannot rotate this carbon to this carbon, you cannot do the rotation. So please understand that one molecule here cannot be converted to another geometrical isomer due to rotation. That is not possible. Both are two separate molecules, and if you compare them, they have the same molecular formula and everything, but only thing that is changing is their spatial orientation is changing. That is, one atom may be in the upper plane and the other atom in the same molecule, the same atom will be in the lower plane. So because of this difference, we say these two are geometrical isomers. Okay, so let's see here the definition. Stereoisomers which cannot interconvert at room temperature. Why it is not able to interconvert the same molecule? Due to restricted rotation. How this restricted rotation is coming? Due to the pi bond. So pi bond, you know, it is formed due to p orbitals, correct? So these p orbitals have lateral overlapping, and because of this lateral overlapping, it cannot rotate actually. So interconversion is not possible due to rotation. So such a type of compounds we together call that as geometrical isomers. Now the question here is, who and all will show geometrical isomerism? We can see here geometrical isomerism is shown by alkenes, because alkenes, you know, there is carbon-carbon double bond is there, and you can see one valency in the upper plane and other valency in the lower plane. Here also one valency in the upper plane and other valency in the lower plane. And now the next class of compounds is oximes. Very, very important. Here you can see carbon nitrogen double bond is present. Please remember, carbon nitrogen double bond is present in oximes. Carbon carbon double bond is present in alkenes. And the third class of compounds which exhibit geometrical isomerism is azo compounds. That is, nitrogen nitrogen double bond is present. Understood? So nitrogen nitrogen double bond is present in azo compounds. So these compounds will show generally the geometrical isomerism. Okay, now we will try to see the geometrical isomerism in alkenes in detail. So let's see that. Now, first of all, what we are going to learn here is we are trying to understand what is the condition for geometrical isomerism. So if you have a double bond, it does not mean that the compound will exhibit geometrical isomerism. There are certain conditions are there that we will try to see first. Okay, so my heading is, please note down the heading, condition for geometrical isomerism. I will write here condition for GI. It's a short term for geometrical isomerism. Please understand, use GI. GI means geometrical isomerism. Okay, so let's see the condition. So I will explain first the condition with an example, then it will be easy to understand actually. So let me draw a compound here, C double bond C. Okay, I will use different colors for your understanding. And you can see here A is connected here. Okay, and I will use another color here, B is connected here. Okay, then I will use C here. Okay, then I will use D here. Okay, now my question here is, what is the condition that is required for this particular compound to exhibit geometrical isomerism? So I can say here that mandatory condition, the mandatory condition here is this carbon atom is sp2 hybridized. Okay, please check that. It will be sp2 hybridized because you have a double bond here. So if I put S, here P, so this becomes sp2, and this is also what? sp2 hybridized. Now the condition here is A should not be equal to B. That means the atoms which is attached to an sp2 hybridized carbon atom should be different. That is, first condition I can say A mandatorily should not be equal to B. So what is the next sp2 hybridized carbon atom? This one. So here also I can say C should not be equal to D and C should not be equal to D. Okay, so this is the very important condition. Now can you tell me what and all possible? If this is the condition, can you tell me what and all things possible? I can say, I will write that with blue color. What and all things possible is A can be equal to C. A can be equal to C or A may not be equal to C. Possible. Okay, these are possible condition. Possible condition. Okay, possible condition. Okay. Okay, this should not, okay, this is, it should be strict, mandatorily not possible. So this condition should be mandatorily obeyed. Then only the compound will exhibit geometrical isomerism. Now possible things are A can be equal to C or A may not be equal to C, or A can be equal to D, A can be equal to D, or A may not be equal to D. It's okay. Similarly, I can write B can be equal to C or B may not be equal to C. Similarly, B can be equal to D or B may not be equal to D. Anything is possible. But please understand what you need to check mandatorily. A should not be equal to B or C should not be equal to D. This you should ensure. If A is equal to B, surely I can say that compound will not exhibit geometrical isomerism. The shortcut for that is, to the same carbon atom you should not have the same atoms attached. If the same atoms are attached to the same sp2 hybridized carbon atom, it will not exhibit geometrical isomerism. Understood? So these conditions you can note down, very important. Okay. Then sometimes, I hope you have noted down, sometimes instead of giving the compound in a horizontal plane, they may also give the compound in a vertical plane. Let's see that. For example, I can draw like this. Okay, then you can see here A connected and here C connected. Okay, and here I am connecting the B and here I am connecting the D. Now tell me, Just I have drawn the same thing in the vertical plane. Now the condition still remains the same. Please look at it. I can say this is the sp2 hybridized carbon atom. If this is the sp2 hybridized carbon atom, to this atom both should be different. So A should not be equal to B. Here also it holds good. Now this is another sp2 hybridized carbon atom. So this one also C should not be equal to D. That is also understood. But they may give in horizontal plane or vertical plane. Now you can say A can be equal to C. Correct? A can be equal to C because both are different carbon atoms. A can be equal to D. A may not be equal to C, or A may not be equal to D. That is not a problem, since all these conditions are possible. But this condition, it should not be possible. If this condition is strictly followed, then only the compound exhibits geometrical isomerism. Clear? Okay. I hope you got a fair idea regarding the condition for geometrical isomerism. Now let's see how to name this geometrical isomers. There are two different naming systems are there. I will explain both. Okay, so you can give the heading nomenclature for geometrical isomerism. Okay, nomenclature for geometrical isomerism. So I will explain, I will give you a rough idea, then I will go in detail regarding the first nomenclature system. Okay. Okay, so all these I am explaining with respect to the first stuff, that is in alkenes. Okay, so in alkenes itself we have, so let me write nomenclature of GI, geometrical isomerism, in alkenes. Okay, so let's see what are they. Now I can say there are two systems we are following. Okay, the first system is called cis-trans nomenclature system. It is a cis-trans system, that is more correct. Now the next one here is EZ system. So the next one is E. Okay, what E stands for? Entgegen. So you can say Entgegen. And EZ. EZ stands for Zusammen. So Zusammen. Okay, so there are two systems. So the first one is cis-trans system and the second one is EZ system. So let's see in detail. Okay, let me say why we need two systems, then you will understand, okay, why they have proposed two systems. The cis-trans system they are introducing whenever, I can say, if you have a carbon-carbon double bond, okay, into that you are connecting A, B, C and D. Suppose A may be equal to C. In that case, or B may be equal to D. In that case, they will use cis-trans system. That means there are identical atoms are there. But ensure that the identical atoms are not on the same sp2 hybridized carbon atom. So here A can be equal to C or B can be equal to D. In this case, we use cis-trans system. I hope it is clear for you. Now, in that case, cis-trans is sufficient, right? Then why they went for EZ system? Understand that suppose you have the same carbon atom and A, B, C and D are there. But here all A, B, C and D are different. In that case, they use EZ system. Now the question here is, all are different, then how they assign E and Z? I will teach you how we can do that. Cis-trans also I will teach you in detail, but now I hope you understood where we need to apply cis-trans and where we need to apply E and Z. Okay, I hope it is clear for you. Okay, now let's go in detail the cis-trans system. Okay, so we will go in detail the cis-trans system of nomenclature. So very simple, cis-trans itself I say, we can say classify the given molecule as either cis form or we can classify the given molecule as trans form. How we will do that? Let's see with one example. So you have a C double bond C, C double bond C, okay, and you have a compound A here and you have a compound B here. Okay, I will take another color, then it is easy to understand. Okay, you have here B. Okay. Now you have a compound A here, same A here present, and you have a compound B here. Now let's see here. If you look into this system, can you first tell me whether this will exhibit geometrical isomerism or not? So how to check that? You can see here, this is my sp2 hybridized carbon atom. So it has one atom as A and another atom as B. Both are different. Okay. So if you see at this sp2 hybridized carbon atom, this has one atom as A and another atom as B. Both are different. So to both sp2 hybridized carbon atom, atoms attached are different in nature. So this will exhibit Gi. And now how I will assign whether cis or trans to this? Please see here. Now if I look at the A atom, it is above the plane of double bond. Now if I look at here at the sp2 hybridized carbon atom, here also A is above the plane of C. So if both are above the plane, similar atoms are above the plane of the double bond, then we say this is a cis system. Okay. So here also if you see, here it is B, here it is B, that is connected below. Here also it is connected below. Both are connected below means it is B system. So that means identical things are connected. Both A are connected above and here both B are connected below. And sometimes both A may be connected down and both B may be connected above. Then also it is cis. So the conclusion here is identical atoms should be lying in the same plane. Understood? Here B is also lying in the below plane. Here both A are lying also in the above plane. Then we assign the name cis isomer to this particular compound. Okay. Now let's see what is trans. So in trans, the difference is, you can see here, you have a carbon-carbon double bond. Okay. So to this system, let me connect A here. Okay. Then A is in the below plane here, and let's connect B here, and you have a B in the down plane. Okay. Now if you look at this system, you can easily see here A is in the upper plane, but in the next sp2 hybridized carbon atom, A is in the below plane. Here if you see, B is in the above plane, but in this sp2 hybridized carbon atom, it is in the here it is in the above plane, here it is in the below plane. Like that, if this is differing, then we say such a system is trans system. Okay. So I hope you got a fair idea what is cis-trans system. Now we will see real examples to understand the same. Okay. So we were discussing cis-trans isomerism, right? So let's see some of the examples of cis-trans isomerism. So these are real world examples. You could see this compound. So can you tell me what is the type of system here? So you could see carbon-carbon double bond is there. So this is sp2 hybridized. Okay. And this is also sp2 hybridized. Now let's see. So to this carbon atom, both atoms are different, bromine and chlorine. And to this carbon atom, both atoms are different. So I can say there is geometrical isomerism here. Now if you compare this, you can see here bromine is above plane of the double bond. And here if you see, it is in the below plane. And here if you see, chlorine is in the above plane in this sp2 hybridized carbon atom, but here if you see, it is in the below plane. So we know that if they are linked like this, this should be a what system? Trans system. Correct? Now let's see the example 2. So here also first we need to check both are sp2 hybridized. Correct? This is also sp2 hybridized. Now if you see here, to this carbon atom, one is a hydrogen atom and another is a methyl group. To this carbon atom, one is a hydrogen atom and other is a ethyl group. Okay. Now if you see here, both similar atoms are on the upper plane. Here hydrogen atom is on the upper plane. Here also hydrogen atom is on the upper plane. It is not mandatory that this should be equal to this. And both heavier groups are in the below plane. Okay. So if you see here, both hydrogen atoms are in the same upper plane, means this should be a cis system. Understood? Now if you go to example 3, now you could see it is represented vertically. Now let's see, this is one sp2 hybridized carbon atom and this is another sp2 hybridized carbon atom. So if you see in this one, you could see both atoms, one is a CH3 group, other is a chlorine, both are different. So in this one is a chlorine atom and another is a CH3 group. Both are different. So Gi exists. So here, if you see, this is the double bond plane. So in this double bond plane, chlorine, it is in the upper plane, and here the chlorine, if you see here, you could see here, this is in the left plane, I can say, this is the double bond. So this is in the left plane and this is in the right plane. So both are different. So here CH3 is in the right plane and this is in the left plane. So they are also opposite. So this means it is a trans system. Okay. Now let's go to the example number 4. In example number 4, I am checking here 2 sp2 hybridized carbon atom can be seen. This is one and this is another one. Okay. So this carbon atom, both atoms are different. But when I am checking this carbon atom, both are similar. That means this compound will not exhibit, will not show GI, will not show geometrical isomerism. Understood? So these are the examples you can note down. Very important just to understand this. So next we will try to see the properties of cis-trans isomerism. That means if I have a cis isomer and a trans isomer, and if somebody is asking you to compare the dipole moment of cis and trans, which one will be having a higher dipole moment or which one is having a higher solubility, like that. So you should be able to comment cis is having high or trans is having high. So I will give you a generalized output for that. Okay. Now let's compare the properties of cis-trans isomers with respect to the following parameters. So the first question here is stability. If you compare the stability of a cis isomer with the trans isomer, which will be having more stable nature. So I can say here that always the trans form is more stable than cis form. I will explain why it is like that. So I will say trans is having a greater stability than cis. So why it is like that? Let's see. So let's take an example. For example, C double bond C, you have a chlorine here, you have a chlorine here, here you have a bromine, here you have a bromine. Now if you see chlorine, it has lone pairs, chlorine it has lone pairs, bromine also has same thing. Okay. So if you see here, these chlorine atoms, they are similar atoms actually, size as well as everything is similar, and they are in the same plane. Correct? So since they are in the same plane, what will happen? Here if you see bromine atoms are also in the same plane. Because of this similar plane, I can say these will undergo some sort of repulsion every time. Because of this repulsion, what will happen is the stability of this isomer will get affected. So we say that, we know that this isomer is what actually cis. But if I draw a transform, for example something like this, you have a chlorine here, you have a chlorine here, you have a bromine here and you have a bromine here. Now if you see this, the similar atoms, they are very much far apart in a trans format. So that means similar atoms, as you know, similar charges, as they repel, similarly the similar atoms will also repel, but here it is far away. So we can say that usually the cis isomer, usually the trans isomer is being more stable than a cis isomer with respect to what point of view? Stability point of view. Clear? Now let's say the next feature, that is the dipole moment. So let's see for dipole moment which one is more, which one is having higher dipole moment. So if you compare dipole moment, I can say cis form is having a greater dipole moment than trans. Okay, cis form is having a greater dipole moment than trans. Why it is like that? Let's compare. Now if I am drawing a figure CH3CH, okay, double bond C. So let's see CH3 here and here H. Okay. Now if you compare this, you know that this is a cis format. Now I am saying we know that all CH3 groups are what sort of group? Electron repelling group, correct? It is having plus I effect, or it will donate electrons. So what happens? Because of that, electron movement will be in this direction. That means you can say negative charge is concentrated here, correct? Now we know that for a dipole moment, in what direction we draw the arrow? From the plus charge to the minus charge. So we can say here plus charge will be there. So the dipole moment direction is in this direction, correct? So if you see here also the dipole moment direction is in this way, because here plus charge. Now if you see here, both the dipole moments are in same direction. So same direction means, for example, here the dipole moment is mu1, here it is mu2. We know that the net dipole moment will be what? Square root of mu1 square plus mu2 square, 2 mu1 mu2 cos theta. What is the angle between that? You might have learned it's a vector quantity. Understood? So it will be having a net dipole moment. So I can say the dipole moment of this system is not equal to 0. So this is what sort of system? This is a cis system. Understood? You can even take another examples. Instead of CH3, suppose chlorine is there. So let me draw another example so that you will get one more fair idea. So for example, suppose the system is like this. C double bond C. You have a chlorine here and you have a hydrogen here. You have a chlorine here and you have a hydrogen here. Now if you see here chlorine, what sort of group it is? It is electron attracting group. So it will attract the electrons. Because of this, electrons will move in this direction. So there will be net minus charge here and plus charge here. So the dipole moment direction is in this direction. So this here also the same thing will happen and the dipole moment direction is in this way. So if you see here, this is what sort of system? Again, this is a cis system. So if you see, the net dipole moment is in this direction, and if you calculate, you will get some value for dipole moment. So that means the dipole moment, the net dipole moment is not equal to 0. Understood? Now the same system, if you try to do it for a trans, how it will look? Let's see. So for a trans system, if you see C double bond C, okay, chlorine here, here chlorine, so here hydrogen and here hydrogen. Now let's see. Now itself you know that electron here will move in this direction, so here minus charge, here plus charge, so there is one dipole moment in this direction. And if you see the next chlorine atom, it will move the electron in this direction, so minus charge here, plus charge here, so the dipole moment direction is here. So if you see, one dipole moment is moving from center to the left, correct? The other dipole moment is moving from center to the right. So if you do this, it will get cancels off. That means the dipole moment is less or 0. It can happen. So we say dipole moment is equal to 0. This is what sort of system? It is a trans system. Understood? So that is the reason why we say dipole moment of cis is greater than that of trans. I hope you got a fair idea. Okay. So let's say the next feature, that is the polarity. If you know the dipole moment is there for cis system, can you tell me what is the nature for polarity? I can say cis form will have a higher polarity than trans. Can you tell me the reason? Because you know that if dipole moment is higher for a cis system, dipole moment happens because of charge separation. So greater charge separation is there for cis format. So you know that polarity associated with plus and minus sign. So if there is, which one will be greater, more polar? It will be the one which is having higher dipole moment. So surely cis will be having a greater dipole moment, greater polarity than trans format. Understood? Now next becomes, next we will discuss the solubility. Now solubility, when we are discussing, we can say that water, it is polar in nature. So can you tell me which one is more polar here? Cis form. So to dissolve in water, you need to be polar. Because if you are polar, if you are having plus or minus charge separation, it will attract to that particular substance in which it is soluble and it will get immersed in that, or the solubility is high. So because of the higher polar nature of cis, I can say it will also have higher solubility than trans. So cis form will have higher solubility compared to the trans format. Okay. The reason being the dipole moment. Actually, dipole moment is the root cause for polarity and solubility. If the dipole moment is high, the solubility will also increase. Understood? Now let's say the boiling point. So boiling point is also similar to that. So if the compound is more polar, that is there is more plus and minus sign is there, you know that that compound will get attracted to the solvent very fast. Okay, in that case you need to give more amount of heat to get it converted to vapor state. So because of higher solubility of cis, if the solubility is very high, means you need to give more heat to make it vaporize. So we can say even boiling point of cis form is greater than trans. Now last comes the melting point. Melting point is totally different. Here melting means it is a reverse of boiling. That means the molecules should come together and get closely packed. Then only melting will happen, or we say it will convert to solid. heat is removed. So in this case I can say, because of the repulsion of the cis format, it will always try to repel, so that close packing will not be possible in the case of cis format. But in the case of trans, the repulsion is very less, stability is very high, so it can be closely packed. So in that reason I may say melting point of trans is greater than cis. Clear? So I hope you got a fair idea regarding the properties of cis-trans isomerism. So next we will try to see the next system of nomenclature, that is the EZ system, N-Gegen and Zusammen system. Okay.